This is Unit 4, Section 4.3. We're going to talk about our probability rules. And so we talked about the definition of probability, how to interpret them, and then how to simulate them. So today we're going to look at some more rules based on probability. And then we'll get ready for our quiz. All right, so 4.3. We have a sample space S. And so this is where we have our notation for all possible outcomes of a chance process. So if I was thinking of a set that was maybe rolling a dice, I could have outcomes of 1, 2, 3, 4, 5, and 6. And those are my curly brackets. I'm just bad at making them. If I had the set of what it would look like for tossing a coin, I could have tails or heads. I'm going to try. Yep, okay. A probability model is something that we're going to describe that says a description of some chance process that consists of a sample space, so these outcomes, and a probability for each outcome. So if I wanted a model, I could have heads and tails, and then the probability associated with each one as 1/2 and 1/2. Or I could go 1, 2, 3, 4, 5. And these are a fair die, so I would say 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. And this whole thing would now be a model for those probabilities, listing out each outcome and its possibilities here. When we talk about a probability model, it has all the possible outcomes because it's consisting of the sample space. If I'm interested in one particular outcome, this is going to be an event. So it can be all of them, or 1 or 2, or any collection of outcomes from the chance process. So it's a subset of the sample space, usually denoted by a capital letter like A or B. Or I could say, what's the probability of T? And now this event is what is happening in this chance process of flipping a coin. When we look at something that's called mutually exclusive, so this is something that debaters use frequently when they're saying, these two events are mutually exclusive. So your plan doesn't influence mine or impacts mine. They can happen at the same time. Mutually exclusive means these two events have no outcomes in common and never occur together. It is impossible for them to occur at the same time. So that would be if I flip a coin, what's the probability of getting heads and tails? Well, that could never happen. So we would say those are mutually exclusive. You're either one or the other. Complement is an event not occurring, denoted by a superscript of C, like of an event A complement or B complement. So if I said T complement, that would be heads. If I said 1 complement on the dice, that could be a set of values of 2, 3, 4, 5, and 6. This would just mean not 1. And so we read that C as either complement or the word not. All right, so let's look at an example where we're rolling dice. It says many board games involve rolling 2 fair 6-sided dice. Imagine a game asks you to roll 1 green die and 1 red die on each player's turn. Give a probability model for the chance outcome. And so here is our sample space. Here's all the possible combinations we can have of the green and the red die here. And so we can have 1, 1 all the way up to 6, 6. And so we have 36 different possible outcomes in our sample space. So a probability model here would be if we're adding them together, we're subtracting them, we would want to find what outcomes are more likely, less likely, and things like that. So each one of these would have 1/36 as its possible outcome. If they were both the same color, we would have more than one because 1 and 6 here would be the same as 1 and 6 here. But because we have a green and a red, this is not actually the same outcome. So we kind of want to consider what our possible outcomes are. Right now we have 1/36 chance to get any one of these here. So, and that's kind of what it continues and talks about here. Because the dice are fair and each outcome is equally likely, the probability of any of these 36 events occurring is 1 in 36, or 1 out of 36, or even as our decimal here. So what if we define an event A as the sum is 5? What is the probability of A? Meaning, what's the probability that event A occurs? So the probability, and then parentheses, here's our event A, which is called sum of 5. Okay, we put our sample space here down at the bottom, and then we want to go through our list and see how many ways can I make 5. So I have one way here, here, and it's kind of getting me that diagonal. So along all of these is where I can get a sum of 5 on my 2 dice. So if I simplify that, I can get 4 out of 9, or I could say my probability is 0.11 repeating, or about 11% chance of getting a sum as 5. On the second part, it says, what's the probability that event A does not occur? And so again, that's that complement notation here. So if I wanted to find this, okay, now I'm trying to count out what's the probability of an event not occurring. So I have 4 here, which means I would have all the other ones are not 5 of sum, or a sum of 5. So if I add up all of those, I would get 32 of them that are not a sum of 5, because I only have those 4. And so this is going to start relating us to one of our basic probability rules we'll talk about here in a second. But right now, we would just be counting out each one of them. That would simplify down to 5 out of, or I'm sorry, let's divide that. 8 out of 9. Good grief, my subtraction's off here. We get the 0.89, and I don't know why in my head I'm not simplifying that. Divide by 4, we get 8, divide by 4. Oh, that's why. I was like, this is not making sense. There's my 1 there. Whew, all right, now that makes sense. This was my mistake, not that one. I apologize, so let's correct that. 4 out of 36 simplifies to 1 out of 8, and I knew I wanted that 8 out of 9 there. Neither here or there. I've corrected that. All right, on our next part, it says define part B, event B, as sum is 6. So what's the probability of B, sum is 6? Or what is the probability that event B occurs? So out of our 36 options, if we look at sum of 6, now we're on this diagonal, 3 and 3, 2 and 4, 1 and 5. Now there's 5 options out of 36 that will make a sum as 6. And so this one is more likely to occur at 14. And so our next question follows up looking at both events A and B, and it asks us, are they mutually exclusive? So when I looked at event B, and we had event A, sum of 4, sum of 5 here. Here's event A. Are they mutually exclusive? So mutually exclusive are 2 events that have no outcomes in common and never occur together. So when we look at our 2 outcomes, they don't have any outcomes in common. They never occur together. So we would say yes, because A and B, those 2 events cannot occur at the same time. And if we think about it, we can't roll 2 dice and have them sum up to 6 and sum up to 5 at the same time. So what we could do for notation-wise, we could say the probability of A and B, so those happening together, there's 0 outcomes out of 36 that are A and B. They're mutually exclusive. There's nothing no overlap here. And the last part for this one, it says, what's the probability of A or B, or the probability that event A or event B occurs? So now if I was thinking about probability of A or probability of B, this would lead up to a rule that we could say, okay, well, the probability of A happening, we have 1, 2, 3, 4 out of our 36, plus our event B could happen, because this is the or part, and there's our 5 out of 36 happening. So when we add those together, we get a 9 out of 36, or a 25% chance that either the 2 dice add up to 6 or the 2 dice add up to 5. That leads us to kind of these basic rules. And so we've applied our basic rules in an example with the dice, but here we can formalize them a little bit more. And so our basic rules here say that the probability of an event occurring has to happen between 0 and 1. So here's our first basic rule. We cannot have a probability that's negative. We cannot have a probability that's greater than 1. The second rule says all possible outcomes together, so in our sample space, have the probabilities whose sum is 1. So if I take P, the probability of all the outcomes in our sample space, that should equal 1. So when we look at this one, if I added these two together, it would equal 1. If I added all these 6 together, it will equal 1. That's a rule for any probability model. And the next one on here, it says if all outcomes are equally likely, the probability of an event occurring is the number of outcomes corresponding to event A out of the total number of outcomes in the sample space. So that's where we were finding how likely is it to get a sum of 5, right? That is our numerator. How many total options are there in our sample space? That's our denominator. This one was one that we could have applied, and so I know that sometimes when we're counting, like on here where we had, what is the probability of this one where we had 4 out of 36, and then if we counted all 32 here, what we can look at when we have the complement rule says the probability that an event does not occur, that's our complement, is 1 minus the probability that it does occur. So if we have the probability of A complement or not A, this is 1 minus the probability of A. So if we looked at our example here, we could have said, what's the probability of not A? Well, that's 1 minus the probability of A occurring. And so when we simplify that, that's where we could also get that 32. Subtracting and rewriting this as 36 over 36 to get our 32 out of 36 that we got here, counting up all the options that were not A. And our last basic one says if 2 events have no outcomes in common, that's our definition of mutually exclusive, then the probability that one occurs or the other occurs is the sum of their individual probabilities. The probability of A or B is probability of A plus probability of B. All right, so these are the basic rules. We're going to start looking at some special cases. What happens if the 2 outcomes are not mutually exclusive? What happens if we have more than one event occurring? What if they happen in different orders? Those are all the things that we're going to be talking about as we continue in this unit. Our example to start us out, it says distance learning courses available online are gaining popularity among college students. Maybe not this year. The ages of many randomly selected undergrad students who are taking at least one distance learning courses were recorded. Here's the probability model. All right, so we had 18 to 23-year-olds, 24 to 29, all the way up to 40 and older. The probability of each group, so 57% of the online learning students are 18 to 23, all the way to 12% of them are 40 and older. Show that this is a legitimate probability model. All right, so legitimate probability models does that mean I have all the sample space? Have I observed all the possible outcomes? So that's correct. We have over 18. I haven't missed any years or skipped anything, so I have all of those. And then we can show that the sum is 1. And so if we add 0.57 plus 0.17 plus 0.14 plus 0.12, when we add those on our calculator, we get 1. So that checks us off as well. Double check. I don't want to say that and then have it have a typo. We get 1. All right. So our follow-up question says, find the probabilities in 2 different ways that a randomly selected student is not in the traditional college age group of 18 to 23 years old. Okay, so we're looking for the probability of someone that is not 18 to 23 years old. And so if I wanted to calculate that, 2 different ways. So we could do not 18 to 23 would be here or here or here. And because your age puts you in each one of those categories, these are mutually exclusive events. You can't be in this category and this category, no matter how hard you're trying. And so when we add those up, individual probabilities, we don't have any overlap. So we can add those together, and this is where I got 0.43. So there's a 43% chance that if I randomly selected somebody out of my online learning courses at the college level, they would be someone that is not a traditional college age student. Another way that we could have used our basic probability rules to say not 18 to 23 would be taking our complement rule, would be 1 minus the probability that they are in this group. If I subtract those, I still get the same 43% chance of not being in the traditional college age group. On our last example, it says randomly select a student who took the 2010 AP Statistics exam and record the student's score. Here's the probability model. So they could have a 1, a 2, a 3, a 4, or a 5. And again, these are mutually exclusive events because you can't get a 5 and a 1. They're not going to do that to us. So our legitimate probability model, we have all the possible outcomes. So we do have the sample. And then we have the sum is equal to 1. So we can check that. 0.233 plus 0.183. And adding up all 5 of these probabilities to show that it is legitimate. And I will double check this before I check it off. So 0.233 plus 0.183 plus 0.235. And I get 1. So because that equals 1, I have a legitimate probability model. So our first question says find the probability that the chosen student scored 3 or better. So our event is 3 or better. And so if we're saying 3 or better, it could be a 3 or a 4 or a 5. So if we had this, we could also write it this way as well. And because these are mutually exclusive, we can add those up. You can't have any overlap. So we'll take the individual probabilities of the 3, of the 4, and of the 5, and add those together to get 0.584. So in 2010, there was a 58.4% chance that you would pass getting a 3, 4, or 5 on the AP exam. The last question says, find the probability that the chosen student didn't get a 1. Okay, so this would be, what's the probability of not a 1? We could have written this as 1 complement as well. So again, different ways that we could have found this. We could have said, okay, not 1, and added up 0.183, 0.235, 0.224, and 0.125. And so this will get us the 0.76. 7, I think is what my calculator says. Or I can use my complement rule and say, okay, everything but this. So 1 minus the 0.233, which also gets me the 0.67. You don't have to show both methods, but sometimes when we have lots and lots of different outcomes in our sample space, we want to know that that's an option when we have it. All right, so these are the basic rules. And so these are things that we're going to refer to as we continue. So we might have 1 missing in our probability model. We can subtract from 1 to find what's left over. That's going to be the missing probability. We might have events that are not occurring using our complement rule. And then the big idea here, putting together the idea of mutually exclusive with this or idea. So we'll start looking at those as well. Let me know if you have questions here and I will help out.